Okay, hello everyone. Thank you for being with us today. It's great to see you all. As you know, with these CIS Get to Know Your Neighbors seminars, we strive to provide a platform for cross-school exchange here internally at EPFL. Last month, we had the pleasure to host Professor Zahand Rahi from Basic Sciences. Today, we are delighted to have Professor Devis Tuia from ENAC with us, and he's going to give us a talk entitled Machine Learning on the Earth System with Remote Sensing. Just a brief recap. So in total, the seminar will last for approximately 1 hour. Devis will present 40 to 45 minutes, and then we have time for Q&A. If you have any urgent questions, put them right in the chat. Devis can see them, so maybe picks them up. Otherwise, we'll have time at the end to address all the questions. You might also have the time to ask your questions directly when unmuted. Before I dive into the presentation, I would like to thank Devis, of course, for his availability, and the entire team again for the organization of the event. Devis, the screen is all yours.
Thank you very much, Jan. I'm not 100% sure I will be able to see the questions, so in case I miss them, just tell me, and I'm very happy to stop and have a look. So hello everyone, and thank you very much for coming today. It's good to see you, even though it's not the same as having been all together at EPFL, but okay, we do what we can, and we do it remotely. All right, I'll now share my screen. Just please, Jan, confirm that you can see everything.
Looks pretty promising. Yes, all fine.
It's looking okay. Oh, I can
Yep.
even see the chat, so it's fantastic. Very good. Okay, so let's get started. And so it's my pleasure in the next 40 minutes, more or less, to talk about the Earth with all of you, so that you can see in this first slide. So this our blue planet that provides for us everything we need. And basically, the story I want to tell you today is how to use remote sensing technology, so mostly satellite imaging, aerial imaging, in order to monitoring things that happen at the surface. And of course, I'm not talking of sensor that is as far as the one we see in this image. So this very famous picture was taken from the moon, so 400,000 kilometers from here. So I will mostly talk about something that looks a little bit like that. So sensors that are way closer to where we are, and so maybe something between 100 meters above our heads if we're talking about drones, up to 700 kilometers if we're talking satellites. And the images we will be looking at in this 40 minutes will look a little bit like this one. So this is a satellite view of a neighborhood of Zurich called Brutisellen. If you're from there, maybe you know where it is. And basically, but we can observe Earth thanks to remote sensing, but in different waves depending on the sensor we use. So an image like that could, for example, be acquired by a digital camera. So like your favorite reflex camera, you could put it on a balloon or on a drone, and this camera will be able, give you some red, green, and blue signals about what's happening at the Earth. But in remote sensing, we're very happy to design and send to space sensors that have more than that, so that they have some additional bands, like in the case here in the middle, when we see QuickBird, which is an American satellite that gives you an additional band. You can see here a near infrared channel, which is very well separated from the color ones. And then you have a whole spectrum of sensors that are orbiting over our heads, and they can go from multi-band sensors all the way to what we call hyperspectral sensors. And in that case, we have like very, very narrow spectral bands that scan the electromagnetic spectrum every 10, 20 nanometers. And this will give you like a very, very fine-grained description of what's happening on Earth. So thanks to that, basically, if we are able to look at images like that, but maybe in another way. So maybe you have noticed the image behind me, or the one that is now on the screen. These are like images that do not seem suspicious to remote sensing scientists, because as absurd as it may sound, for us, vegetation is red. And this is simply because remote sensing, in remote sensing, we tend to put infrared information in the red channel of the screen. And then since vegetation reflects a lot in the infrared, everything that is vegetated will become red to our eyes. So, I mean, for my daily business, trees are red, which is, you know, maybe a bit strange, but just stay with me on this one. But of course you can then put the band that you want in your channels of the screen, and you will see different colors that will help you in solving a number of monitoring tasks that I will show you in a second. But coming back to our different sensor, basically the difference will be that with the digital camera, for 3 green surfaces, you will have basically 3 numbers, one in the blue, one in the green, one in the red. But when you start to have infrared, you will maybe be able to differentiate vegetation from green roofs that will not react in the infrared. And if you go to hyperspectral, then you will have a complete spectral signature, so meaning 1 point every 10, 20 nanometers for that specific pixel. And this will help you, you know, understanding water absorption, understanding chemicals, maybe carbon, and so on. So we have all these guys at our disposal, and today I will talk mostly about these two, so digital cameras and multispectral, for a number of reasons. The first being that these are the ones that are mostly accessible. So these are the data that is maybe easier to lay your hands on, and also because hyperspectral is still, you know, in a very exciting phase of development, but you maybe won't find as easily sensors and images to do hyperspectral image analysis. Maybe someone in the audience is into hyperspectral. I did my PhD on that, but you know, it's still not as much penetrated in society as the other types of sensors. Okay, and another thing that makes it interesting is that a lot of things have changed in remote sensing since the very beginning. So in the 80s, so when the first Landsat, when the Landsat program was really taking up speed, well, you had to pay a lot of money to have one image. So it was roughly $4,000 in the 80s. And you know, the price of the images went down and down and down, but still at the end of the century, 1999, you still have to pay $500 for one satellite image. So I mean, this means that you could not have many of these, and also, you know, you had to open your wallet if you want to make some monitoring. So it was not so easy to have a boost in research. And then there was not so much computational resources around, which made that, you know, remote sensing research was stalling a little bit. But then basically what happened is that Landsat decided to open for free all their images, and this was like a terrific boost for research in remote sensing. And it basically boosted the private industry to send satellites in space. So nowadays we have almost 1,000 Earth observation satellites in orbit. And I remember giving a slide like this one 5 years ago, and I was very excited because we had 300. So, I mean, the thing is really taking speed, and especially thanks to microsatellites, this is accelerating even more. And resolution is getting much better. So if you look at Landsat versus what is currently done from space by the formerly Digital Globe, now Maxar satellites, you can see that like spatial resolution is getting much more interesting for analysis. And in terms of free data, well, the European Union is disclosing a ton of data, honestly. So in the Sentinel program, and it's basically 2.5 petabytes of images per year with the satellites that are actually orbiting, and they're planning to send a number of additional ones in space in the next years. And this is without talking about drones. And if you go drones, then you can imagine the mass of images that is at your disposal. So basically, there is a lot we can do with satellite imaging. And then, you know, when I was talking about this free satellite images from the Sentinels, you need to expect something that looks like that. So this is what you can retrieve from the Google Earth engine, which is basically a huge data cube of Sentinel images, Landsat images. And then you start to really have time series of satellite images that, you know, allow you to monitor in space and time what is going on at the surface of the Earth. So basically, this video will go on for a few minutes and show you several locations and the different images. So here we have the Pearl River Delta in China, and you see that from the 80s it has changes really a lot, and cities are developing. I mean, I hope like this is triggering curiosities for the different things you can do with remote sensing nowadays that, I mean, you could not do, 10 years ago. There was not so much images that we could use unless you were buying images and so on. And let's look at Las Vegas because it's really impressive, and then we move on. So just look how much Las Vegas has changed. So it seems that people like casinos very much, huh? But okay, so and all this is available for free, and this really like enables a lot for remote sensing research. And thanks to this data, thanks to a lot of cloud computing that is nowadays available, or the GPUs that we all have in our computers now, I mean, there is now a lot we can do, especially as machine learning researchers, in order to extract information out of these images to make a change. And for me, the change I want to make is more in terms of environmental monitoring, because this is relevant. Because, for example, when you have a catastrophe, I mean, if you have access to remote sensing images, then you can map affected areas, for example, and very quickly deploy rescue teams at the right place. Just imagine if you were blind, I mean, not blind in the sense that you don't see, but blind in the remote sensing sense, so that you don't know where there are affected buildings and you don't know where to send rescue teams, you become way less efficient. And of course, this is something that people usually do in intervention centers, but you need to imagine a place where they put 20 people in a room and they look at satellite images and manually try to find the areas that have been affected. And this is very inefficient, actually. If we can design algorithms that do that automatically, so based on machine learning, typically, well, we can really make a difference here and save people in distress. And it's not only about disasters. I mean, if you can image it, you can map it, you can detect, and so on. So, I mean, there is a number of things you can do, going from animal monitoring. I will be talking about it in a second. Forest monitoring globally, or I mean, even you can work for the economy and monitor activities that can be like parking usage, solar panels, and so on. Like one EPFL startup called Picterra that is basically offering a lot of deep learning based system to use satellite images to basically detect things that you are interested in. Okay, so I mean, this was like kind of a very quick introduction on the different things you can do with remote sensing and satellites. And for the rest of the talk, I would like to go a little bit more into different algorithms that we've been developing in my former and current team, in order to see how we can develop interesting solutions to monitoring processes that happen at the surface of Earth. And I'll do that in two parts. So one, we will talk a little bit about mostly pixel-based products. I don't want to spoil too much. And then I'll go to more prospective things, so things I'm working on at the moment that are a little bit less like finished stories, but more like open-ended discussions on funny things we can do with remote sensing. Okay, so I mean, basically the question is, I mean, if you had access to images like that, what would you do? No, and I guess everyone in the audience has their own idea. Without going to a real interaction with you guys, because I mean we will have that in a few minutes. But I mean, I guess one of the first thing that comes to mind. I mean, you can write in the chat if you have something that comes to mind. Just write down what you will do with an image like that. But basically, the first thing that comes to my mind would be to do some kind of semantic segmentation. So given the image, let's assign to every pixel more or less what's going on and see if it's a tree, if it's a street, if it's a building, and so on. Of course, you can go much more fine than that, but I mean that's not the purpose of the current discussion. The story is that semantic segmentation is something that is pretty like obvious to do with this type of images, and also people in remote sensing have noticed that. So there is quite a lot of algorithms around that are being developed to, convert pixel values that are multidimensional vector 3 to how much the sensor have bands dimensional ones. and to convert them into semantic maps. So if you Google that, like remote sensing semantic segmentation, you will end up with something that looks like this slide. So you see, I mean, there are a lot of variations of segnet or UNet, and people are mostly looking at how to use the extra bands and how to fine-tune ImageNet-based models. So there is a lot of research, but sometimes it also seems that there is a lot of research, maybe a little bit too much, because the topic seems a little bit exhausted like that. But fortunately, this is not the case, because I mean, there is a lot of things still to be done. So I wanted to spend a few minutes to show you 3 challenges that remain in machine learning for EO. I mean, it's not going to be only semantic segmentation, but I wanted to share with you 3 things that we did that I think are interesting, both for machine learning and for remote sensing, and not just as a technology transfer from one field to the other. So the first challenge is that in remote sensing, we have a lot of data, but we do not have a lot of annotations. So labels are pretty expensive. I mean, let's say quality labels are very expensive, and it's not always extremely simple to obtain large annotated, like ImageNet scale type of labels. And I mean, it's something that is improving over the years. There are like benchmarks that are starting to appear, and even though they can be used to train a remote sensing model from scratch, like multi-bands model from scratch, still they tend to focus on building detection or land cover. So if you're interested in something different, like if you're interested in forests or things like that, then there is not so much around that you can base your models on. And also they're often pretty small. So you have maybe, a handful of images. So then you have like very strong domain adaptation problems, where you train your model on a very specific geographic condition, and then it becomes complicated to move it around to another country or another type of ecosystem. There are, nevertheless, very large databases of labels, like the current land cover that you can see here on the right. But these guys have a little bit the problem that they are very coarse. So if you have images that are like metric resolution, like the one you see on the left here, well, the corresponding labels are pretty coarse because they have been done on images that are lower resolution. So the labels are noisy. And so sometimes it's not really a one-to-one correspondence. So, I'm sure you're having some ideas on how to deal with that. Dealing with noisy label is something very exciting. So, I mean, this opened the door to a lot of potential solutions. But of course, if you don't have a lot of labels, I mean, okay, you can always fine-tune ImageNet type of models, but then you're limited to RGB sensors. And then if you want to go really like infrared multiband sensors, you need to be a bit creative. But if you want to train from scratch, one solution is always to keep like model as small as possible, right? So we want to limit the number of parameters, but still have like very, very successful solutions. So this was, for example, the one that you see on the slide. It's a solution we proposed a few years back to have models that could remain small in terms of parameters. And in this case, we investigated how to achieve that by encoding rotation invariance into CNNs. So basically, we were thinking that in satellite view, I mean, a car is always a car if you rotate the image by an arbitrary angle. I mean, the shadow aside, but I mean, the object doesn't change if you rotate the image. So if you can achieve rotation invariance, you will basically have you will be able to save a lot of space by learning one filter that then you rotate, like in this case here. No? And then by pulling across rotation and not only across maximum activation, we were able to propagate rotation information and then to become rotation invariant or equivariant depending on the design. And of course, we didn't only do that on images of pizza. So I guess that by my accent, you understand why I put a pizza on the image. But okay, so for me, my heart is always in remote sensing. So basically, then when we had this type of logic, we started to apply it to very high resolution imaging. So in this case, we're talking about 3 centimeter resolution aerial imaging, where you have some false color. So remember, vegetation is red, as I told you before, plus height. So we had a very precise height model, and we basically learned a semantic segmentation model that would represent buildings and streets and cars and trees and grass. So these were the classes we were trying to reproduce. And the good news is that we were able to, match, like here in light blue, the performance of state-of-the-art models with a model that was significantly smaller. So if you look at the number of parameters involved, we're talking at 10 to the power of 5 versus 10 to the power of 7 of a state-of-the-art type of model that we were comparing against. So, I mean, the story is that by this reasonably simple tricks, we were able to encode equivariance to rotation, and this allowed us to have models that we could train from scratch instead of relying on pre-trained large models from computer vision. Okay, but okay, so there is a number of things we can do with semantic segmentation, but at the end of the day, the people who will use these maps are often interested in vector shapes. So imagine the cadastre. They need their cadastral plans are shapes that are in vector, because then they go into software that allow them to calculate solar potential, to be modified easily by moving vertices and things like that. So basically, detecting the buildings in a semantic segmentation sense is fine, but then, I mean, you need to do the conversion to vectors, and even though strategies exist to go raster to vector, you always end up with problems of geometry, or if your map is noisy, then it's a little bit complicated to move to the vector shape. So we thought, okay, why not, instead of predicting a semantic segmentation map, why not predicting the vector map directly? And this is something that it's also taking some momentum in vision. So if you're familiar with polygon RNN, for example, you can have some models that like learn where to place vertices one by one and then try to reconstruct a shape. And in our case, basically, we thought of revisiting a classic. So I don't know if you're fans of classic rock, no, it's always the best song, the old ones, no. So we thought, okay, let's go back and take a model that is really cool. So for example, the active contour model or the snake, if you're familiar with that. And these are models where basically you start with a vector shape made of vertices and edges, and you put it in these active contour models, and the model will try to move around the vertices such that at the end of the day, it will correspond to the outline of your object. So how does it do that? It does it by minimizing an energy function. So I don't know if you're familiar with this type of models, I hope so, but they use these energy functions that depend on a number of terms. So this one in particular is the one that we used as a data term that is an edge detector. So it basically will tell you, oh, the vertices should be close to the edges, so minimal energy on the edges. Then it will try to penalize vector shapes that are very long to avoid it to go zigzag. It will avoid very sharp curves, because originally the active contour model was for like round shapes. And then it will have what we call a balloon that will try to inflate the vector shape as much as possible to avoid to have super small object, but try to make them fill the space. Okay, so if you're lucky enough, and by tweaking these parameters here, you can end up with a solution that it's fine. But then imagine if you have to do it for every single building in the world. So every building might have different parameters, and it starts to become a little bit of a tedious job. And also, if you get a result like that, then you're not very happy because you're missing the corners. But I mean, why is that? Which parameters did you set wrong? So basically, the idea here was to instead of setting all these parameters by hand, actually to learn them with a neural network. And we also decided, why not learning the data term as well? Because in the end, we can learn an edge detector that can be even class specific, and that it will like help us making better outlines. And this is the story of what we did. So we designed a convolutional neural network that instead of predicting the vector shape itself, it will predict the different ingredients of the energy of the active contour model. So this means that our CNN will predict these three maps The first being the data term. So it will predict an edge detector and it learn it from data. It will predict a map that will tell you, do not penalize curvature at the edges because you want the sharp edges of buildings, but penalize curvature along the walls because the walls are straight. And another map that will tell you, if you're inside a building, push the vertices out. And if you're outside of it, shrink. And with these three maps, we can put them in an ACM that takes a randomized initialization and will try to make the right vector shape. After this, it will compare it to the ground truth and then have a loss that goes back in the CNN such that the model will predict better terms of the energy function. So we are basically learning the energy function. We're not learning the final task itself, because the only thing the CNN predicts are these maps that the ACM uses to do the right prediction. So it was a kind of it was a fun thing to do because it was a little bit different of the, the usual get image predict segmentation map, but we were like having a new twist on the problem by learning maps that are useful for an energy minimization model. So I found this was very, very fun. And we had some tests on the Toronto dataset that maybe some of you know. So you were some of the very rare lucky guy who could lay your hands on the Toronto dataset. And okay, the result is not perfect, but we're starting to approach building shapes pretty much. So here you have the results of the deep watershed transform. There was like a CVPR 2017 paper. And little by little, we're starting to outlining with vectors the buildings. And I know that the model has been taken in studies in the next editions of Vision conferences. And I mean, the problem is tough because if you look well at it, I mean, even the ground truth sometimes is a little bit questionable. And if you look at this one, for example, I don't know if, can you see my mouse? So I hope so, that you can see my mouse.
Yep.
Yep. And you see, this specific outline is not very precise. So we are learning from here. So it's actually pretty cool that we can have this vector shape that outline pretty neatly the buildings. Okay, the third and last is one I want to show you by bringing you to a trip to Africa. So let's go to better climates, like Alexandra was showing us before, some nice sandy beaches. So in this case, we go in the savannah, and so the third challenge will be that, again, people have often a lot of images. So I work a lot with ecologists, and very often they have millions of images, but they do not have labels. So it's very difficult to actually give values to all these images because somehow they are sleeping there on their hard drives. So people have been, like buying a camera, putting on a drone, and then making flights and acquiring a lot of data. But at the end of the day, to make the census that they need, the thing that could really speed up their work is to have an algorithm that will allow them to detect the animals. So in this case, now we have all the animals, and the story was to have an object detector that would basically put a bounding box around every single one. And this, of course, seems very simple, but there are a number of caveats that I want to see with a little game. So this is the time where you participate. So you can write in the chat or take your mic on and tell me how many animals you see in the image. And you can take a couple of seconds to have a look. So this is actual footage we had in Namibia, so I'm not making that up. So we had 15. Okay, Alexandra, I'm impressed. You're almost correct. Okay. I've left the image too long on screen. All right, so I think everybody has seen these ones pretty well. These ones are also pretty easy to see. But of course, I mean, if you want to get those ones, I will have trouble myself to see those ones. And for example, this guy here is not an animal. It's just a shadow of a tree without leaves. And And this one is not an animal either. So, I mean, the counting problem per se, it's not so simple. And also the story is that the majority of our images are empty, so they have no animals. So basically, to train a detector, it becomes a bit complicated because you cannot really use completely off-the-shelf algorithms. And also, you want to have some kind of iteration where, I mean, your first iteration of the algorithms will end up missing some animals, like the ones here, or it will start to detect trees as animals or things like that. So basically, you want to have something that not only is a good detector for your animals, but also is able to play games with the rangers that know very well the region and scale up to the tens of thousands of images that they will have to go through. So basically, we teamed up with Microsoft, the AI for Earth, and Wageningen University. I mean, we were at Wageningen at the time, so I mean, we didn't team up with Wageningen because we were already there. But okay, and we developed this software, big software tool called AID, and basically, I stop saying basically. I say it every 3 seconds. And this software allows people, mostly ecologists, to load the images of a terrestrial campaign, having some deep learning algorithms making the detection of animals computed on Microsoft Azure on the cloud, and then also has the opportunity to feedback and having some active learning loops where most uncertain image are shown back to the users can update, and this improves the models, and models can be shared among users. And we're trying to basically to build up a huge community of animal ecology models that can go from, you know, image level annotations to counting with point-based stuff, bounding boxes that are mostly something like conservation ecologists or behavioral ecologists are interested in. And then we also sneaked in some semantic segmentation because that's also something we do a lot. And so we could reuse the same software tool. So this type of solution is something that, you know, we have a partnership between us, academia, and industry, and it basically helped us make the difference and reach a lot of ecology scattered all over the world. And AID is now used in several places around the world, and somehow it's the first little break to having a clear picture of what's going on with biodiversity losses, and hopefully maybe also to act against poaching and allowing people on the ground not to get killed when they go look for their animals, because this actually happens. And by doing that with a drone, we can make sure that people don't get too close to the poachers that don't really want us to know that they're there. Okay, so we are, how long have I been talking? 31 minutes, okay? So I think I'll make it on time, Jan. Don't stress. I will get there in 40. And so the last part of the talk, I wanted to show you something about our current research and things that are really going on at the moment. I want to talk about two things briefly. So the first one is to talk a little bit about one thing that I hear a lot when I discuss machine learning with my non-technical partners, which is basically knowing what is going on under the hood of a CNN. So generating trust and try to understand why a model is predicting the way it is. And on the other hand, to make some interaction that is a little bit more accessible to everyone. And in this case, it's going to be something that has to do with processing natural language. Okay, let's start with the interpretable, explainable AI angle. And this whole thing started when we started a collaboration looking at landscape aesthetics. So basically, the problem was to try to predict if a place is considered beautiful or not. And this is very important, for example, for tourism industry, or people who want to go for holidays, and also for everything that is ecosystem service accounting, which is something the European Union cares a lot about. And it boils down to predict for an image whether people will find a connection to it and find it beautiful or not. And even though this is extremely subjective, if you look at through enough images, you will realize that actually it's not so subjective than that. So there are things that come back all the time and that people tend to agree that they are pretty or not. I mean, if you look at these two images here on the screen, I guess everyone agrees that the lake here is much nicer than the power plant. But maybe you're into power plant. I didn't say that this is like a universal concept. But the story was to understand these factors and not only having a regression models that will predict a number given the image. And so we decided to first having a data set that given images will tell us what people think about it. And of course, we didn't build the website itself, but fortunately this exists already. It's called Scenic or Not. And it's a crowdsourcing portal that has been going on for a few years already. And it gives us something like 200,000 images. And for every image, we have 1 till 10 votes, 1 to 10 of the beauty of the picture. Okay, very well. So the story was that we developed a model that not only predicted the final answer, that will be the score for beauty, but it would also predict intermediate attribute concepts that are per se human understandable and explainable. So the story was to have a CNN that will predict a number of attributes. In our case, we pick them from the Sun database, or later on we pick them from Broaden. And these concepts, everybody can understand them. So it's like, is there a street? Is there clouds? Is there a horizon line clearly visible? And by combining them sparsely, we built sparse groups of attributes that will explain somehow why people found an image beautiful or not. And this actually worked out pretty well. So it allowed us to have this, as I call them, easy to understand and to argue with type of explanations. So for example, in this image here, the model find is very beautiful. So it's a score of 7.8. And it's mostly due to this set of factors, that is that because this image reminds you of climbing, it's natural, and it's a rugged scene. So you can really start to see the reasoning behind why the model has chosen this factor. And so it makes it also very simple to see if the model is predicting something for the wrong reasons. And it allows you to understand why a decision is being taken. I forgot to tell you, all these combinations are linear weights, because otherwise you cannot make direct connection between the attributes and the final score. And the same goes for like not so pretty scenes. Like in this case, we have one very negative score participating to the final response. And this is due to this yellowish cluster of attributes. And in this case, we have the fact that it's man-made, it's metal, and so on and so forth. So then it is now time to scale it up, no? And here is when we come back to remote sensing, because so far we have been looking at like regular camera images, but basically we have all these images around, and we also have, as intermediate semantic concept, we can use these land cover concepts that I was showing you before, this scoring land cover type of concept. So maybe they're not perfectly accurate, but I mean, if you go large scale enough, then they will allow us to have a large scale prediction of beauty. As you can see here, we basically predicted the beauty of England from remote sensing data. And natural landscape, because I'm pretty sure there are people who like London, but in this case, we are working on natural landscapes. And not only we can predict the beauty, but thanks to the land cover we have been learning on, well, now we're able to explain why the model is predicting a certain score here and there, depending on the different category of land cover mapping. So we can see, for example, that when it's water related, people like the coast, and when it's like inner water, estuaries, they contribute mostly negatively, but with the exception of little lakes in the Lake District, and so on and so forth. So somehow the thing makes sense, which is actually pretty good, because it means that we are predicting okay accurately, and we can also have explanations that will be sensible for a landscape architect or some urban planner. Okay, last point of the day in the minutes that are left is about interaction. And I will mostly play a second game with you guys, and I will basically ask you if you see this image, and let's assume you're not EPFL professors or researchers or PhD students. I mean, what would you like to know from this image? That would be my question. Like the first thing that comes to mind. And try to think not as an EPFL employee.
Would be what is the, I mean, we all know it's the Rolex Learning Center, but
where is the Rolex Learning Center? That's a good one. And so I will do it even more general than this. So like, where is it? Okay, you guys know it. I know we're all the EPFL employees, but I mean, I would like to have a model that will basically answer me, okay, it's EPFL, right? Second thing, how high are the building? Oh, usually people ask this as a third one. So Martin, you are ahead of your time. So are there other ideas? Come on, I usually get the second one right as well. Don't disappoint me, please. Okay, nobody wants to play. Oh, okay. Oh, how efficiently is the space? Wow, that's very good. That's way too advanced. So okay, so the second question I usually come up with is how many buildings are there on campus? And basically the thing I would like to happen is that the same model without any change will be able to answer and say, I just made up a number, 57, okay? Then I would like to have then this same model be able to understand the question that will not just be like factual on the image content, but I mean, if I want to know, so this relates to Jan's question of how efficiently the space is used. So I would like the model to understand that this is a question about time, go retrieve an old image of campus. So for like faculty that have been here for less than 15 years, look how EPFL looked like, you know, when I was doing my PhD. And, you know, then compare with the current state and tell me, okay, these buildings are new and the others are not. And I mean, if we now go a little bit back and forth, so you can appreciate that the model is basically performing change detection. So it's a model that basically, given a question on images, finds the answer. And I'm pretty sure some of you are familiar with it. I'm pretty sure Amir, at least, and Alexandre are familiar with VQA, visual question answering. And that's basically the second thing that I'm very excited about these days, is to develop models that, you know, make the bridge between people who will be interested in retrieving information from images by asking questions. So it could be decision makers, it could be journalists, you name it. And basically extract a bunch of features from the text with a recurrent, transformers, you name it. And then from the image, some visual feature, put them in the blender, and then having a model that can give you an answer that you can give back to the person asking the question. So it has just started. We're working on that with the European Space Agency, before with the CNES, and it's going very well, but you know, we're just like scratching the surface and there is still a lot to do. But one thing that we have is a decently big data set. So if someone is doing NLP at the moment, that might be something fun to work with in case you want to have, you know, like few thousand images and a million or so questions and try to learn models to make question answering. Here it is. And I mean, for me, that's a very exciting thing to do. Which brings me to the end of the talk, still on time. And so I hope you appreciated everything we can do on Earth images. And it's maybe not the first thing you think about when you think about machine learning and vision. But as a matter of fact, there is a lot of fun things to do, and there is a lot of data. Maybe not a lot of labels, but the sky is the limit, and you can really do something good working with this type of data. So it's like AI for good at its best. So, I mean, if you want to play, my email is here, and get in touch, and I'm here for your question. Thank you very much.
Thank you, Devis. Are there any questions in the audience? Just raise your hand, please. Many thanks. Let me say some words of closing, if I may. So thank you, Devis, for the presentation. Thanks to all of the audience and the questions. So the last things to be done for the seminar is just to remind you of the upcoming seminars we have. We have Professor Michael Bronstein, who is a professor at Imperial College in London, and he's also working as head of graph learning research at Twitter, coming next Monday to our CS colloquium. So this is showing up now. Thank you, Maud. So this is same time as always, Monday, 3:15. I hope you'll make it. It's going to be an interesting talk as well. And then in June, we're looking forward to invite you again for the next CIS Get to Know Your Neighbor seminar, which will be Jörg Schiffmann, who is the head of the Laboratory of Machine Learning and Design. Afterwards, we have other speakers lined up, but we'll tell you about them once we know the titles of the presentations. So I wish you all a great day. Thank you, and I hope to see you all again to our next students. Stay safe. Bye.
Bye.